Okay, welcome to this video on standard form. This is just really an introduction. We have to remind ourselves first that in standard form, numbers are written in the form of a number between 1 and up to 10, but not including 10. Okay, so a number up to 9.9999 times 10 to the power of some integer. Okay, and that can be a positive or negative integer. All right, now we'll start with the 6 questions here on the left, which are just simple conversions into standard form. All right, so if we start with A, that's going to simply be, that we need to move. You see, this is currently the number 5720 with a decimal point here, if you like. Well, we've got to move that point 3 places to make a number between 1 and 10, in this case 5.72. So the answer would be 5.72 as the base, okay? And that has to be then multiplied by 10 to the power 3 to get the decimal point back into the right position. All right. Now, in question B, we just have 7.4. Now, that's an interesting one because, of course, 7.4 is already a number between 1 and 10. So we don't need to do anything other than multiply it by 1. And to achieve that in standard form, we have to multiply by 10 to the power 0, okay? And that's now in standard form. Now in practice, you wouldn't really be writing numbers like that in standard form because it's only really useful for writing very large or very small numbers. Okay, now question C, we have to consider the point sitting at the end here, and it's got to move back 1, 2, 3, 4, 5 places to get between the 4 and the 7. Okay, and that will give us 4.73. Okay, but because of the 5 places we've had to move, we need to multiply that by 10 to the power 5. Okay. Now, question D has a number that's 6 million, okay? So it's going to begin with 6, okay? We don't have to put 6.0, we can just put 6. And then we need to times that by 10 to the power 6, okay? Which effectively moves the point 3 places and then another 3 places, 6 places in total. Okay, now E is going to be a negative power of 10 because the number is having to get 100 times smaller than 9. All right, so 9 would be our base number because it's between 1 and 10, but the points had to move 2 places this way. Okay, so it's 9 times 10 to the power negative 2. Okay, I mean, basically, 9 on its own is 9 times 10 to the power 0. 0.9 is 9 times 10 to the negative 1. And 0.09 is 9 times 10 to the negative 2. All right, so you can see the pattern there. Now let's take F, and in F we have to move the point from here. Let's just show you the working. 1, 2, 3, 4, so that it creates the number 6.21. So the base is going to be 6.21, and that's going to have to be multiplied by 10 to the power of negative 4. Okay, so make sure you can understand how to convert between normal numbers and standard form, and really the other way around as well. Okay, you should be able to write one of these numbers here in standard form into a normal form like this. Okay, now we've got a couple of questions to solve. They're both based on speed, distance and time. That's why I've put this little reminder here. Speed is distance divided by time. And that also means that distance divided by speed equals time. And that's what we're going to need to use here. Okay, but in part A, that's quite simple. We just have to see how far light would travel in 100 seconds. So that's how far it travels in 1 second. That's 3 times 10 to the 8 meters. Okay, so what I've got to do is do 3 times 10 to the 8, which, by the way, is 300 million, and then times that by another 100. Okay, now the effect of that is to change the index from 8 to 10. So the answer is 3 times 10 to the power of 10. Okay, and that's how far it would travel in 100 seconds. Okay, because that number there is 100 times more than 3 times 10 to the 8. Okay, now part B, we have to work out the mean distance from the Earth to the Sun is 1.5 times 10 to the 11. Okay, so that's a distance. How long does it take for light to travel from the Sun to the Earth? Okay, well, we know the speed of light and we know the distance it's got to travel. So to get the time, we need distance divided by speed. Okay, so the time is equal to the distance, which is 1.5 times 10 to the 11. Okay, divide that by the speed, okay, which is 3 times 10 to the power of 8. Okay, now you need to be careful that you're in the right units, and we are in this case because they are in meters per second and meters. Okay, so the answer we get is going to be in seconds. Now just watch carefully how I do this, because first of all I can deal with indices in the same way I would if we weren't working in standard form. In other words, if I was dealing with something like 3 cubed over 3 to the power 7 or something. All right, but I've also got to deal with these numbers here. Now 1.5 over 3 is 0.5. Okay, and 10 to the 11 divided by 10 to the 8 is 10 cubed. So that's what I get first of all. But now I need to adjust that and put it in standard form, because this number here at the moment is not between 1 and 10. So that is actually the same as 5, but because I've made that 10 times bigger, this now has to be 10 squared. 5 times 10 squared. Okay, and it's a time in seconds. Okay, that's S for seconds. Now that of course is 500 seconds, and there is an argument for putting the answer as 500, but given that the question is in standard form, it's also reasonable to give the answer in standard form. Okay, right, on to this question about the distance from the Earth to the Moon. And we've got to find the distance first of all in meters. Okay, well, you've just got to recognize, hopefully, that there are 1,000 meters in a kilometer. So for every one of those kilometers there's 1,000 meters. So I need to take that number and times it by 1,000. So I have 3.84 times 10 to the 5, okay, times 1,000. And 1,000 is 10 to the 3. Okay, 10 to the power 3. Well, if you times those together, you get 3.84 times 10 to the 8. Okay, 3.84 times 10 to the power of 8. And that is the distance in meters. Okay, in other words, it's 1,000 times more than the distance in kilometers. Okay, so that's fairly straightforward. And notice I'm writing down the working as I go with this. Okay, so let me just tidy that up a little bit. Okay, right, and now we go on to the final part of this question B, and it's asking us to do much the same as in the previous question. How long would it take a spaceship to travel to the moon from Earth if its average speed was 400 meters per second? So this is in meters per second. We've now got the distance in meters, okay, and we need to do distance divided by speed again. So what we need is 3.84, okay, times 10 to the 8, and that needs to be divided by 400. Okay, now this is no calculator, this is a non-calculator question, but it's not that difficult to follow this through. I'll show you now. Okay, so that's the division we're doing. Now you may notice that 384 is 16 away from 400. Okay, so 384 over 400 is 192 over 200, which is 0.96 over 100. Okay, so I'm going to just keep that like that for the moment. So basically I'm dividing this by 4 and this by 4, okay, to give me 0.96, okay, which deliberately puts it out of standard form for the moment, times 10 to the 8, okay, and all of that has to be divided by 100. Okay, now 100 is 10 squared, 10 to the power 2. Okay, so if I take 10 to the 8 and divide it by 10 to the 2, I get 10 to the 6. So this could be written as 0.96 times 10 to the 6. Okay, but it's still not in standard form, all right, because of this first number not being between 1 and 10. So I now need to change it yet again and write it as 9.6. Okay, so I've made that 10 times bigger to put it in standard form, but then that has to now become 10 to the 5 to compensate, and that's now written in standard form. And what is it? It is the time in seconds. Okay, now it doesn't ask for it in hours and minutes, but if you needed to, you could convert that if you needed to. But that's the answer in seconds. So that's 9.6 times 10 to the 5 is basically 960,000 seconds. Okay, so it's nearly 1 million seconds, but not quite. Okay, so that's an introduction to standard form using very large numbers. Standard form is often used to represent very large numbers like astronomical distances, or very, very small numbers like the size of atoms and the mass of subatomic particles, that kind of thing. Okay, and that's the end of that video. I hope it was helpful.